Good evening. I'm Stewart Brand from the Long Now board, and I'll take you back 15 years to 1996 when the Long Now board, such as it was then, met in Colorado to think about building a 10,000-year clock. And a guest there was a young man who came up with the idea for a building for this 10,000-year clock. It was quite an elegant spiral. You could go up and then come all the way down without turning around. And it was so elegant, we were so impressed by the design by this trained industrial designer that we hired him as the first employee of the Long Now Foundation. And that was Alexander Rose. I think he was the only employee for quite a while. And then we checked with various of our friends, artists and such, what do you think of this building for this 10,000-year clock? And Laurie Anderson said, looks pretty male to me. And we were chagrined. But then we also started thinking about buildings lasting 10,000 years, and you do a little research, and there's not any buildings in that category, basically. But we really wanted to have a space for the clock that would last a long time, and we started to realize that the research was showing us that spaces underground, things that are buried, last for a long time. But we sort of hated the idea of just making a basement for a clock, be water and it's kind of a downer. So then came the idea of putting it underground only in a mountain. And we figured that would satisfy Laurie. It would be a womb with a view. We can work with that. And then it also started us on a quest to start investigating underground spaces made by people, especially recently, that were intended to last a very long time. And the byproduct of that is that Alexander has been to some peculiar places that almost nobody gets to go, and had thoughts nobody gets to think because of that. And he's here to talk about them tonight.
Thanks, Stuart, and it's thank you all for cramming into our little space here. This is the first time I've given this talk. This is kind of a subset of my usual talk that I've expanded for tonight, so I'd appreciate any feedback on it. And I hope that it can be plenty interactive. I guess we're going to do questions at the end, so please do hold on to them. But if there's some unbelievably pressing question, feel free to shout it out and we'll try and answer it right in the middle. This is also the first time I've given a talk where I'm not explaining what the clock project is. So just show of hands, does everybody here know what the clock project is? I need the other one. Does anybody not know what the clock project is? You have one person, two people, three people. Okay, great. Okay, so I'll just do the very fast version. The Long Now Foundation was started to foster long-term thinking and responsibility, and one of the ways of doing that was Danny Hillis's idea to build an icon to long-term thinking, a 10,000-year all-mechanical clock that people could come visit at a remote site, and the whole process of visiting it and seeing it and talking about that physical object would embody this long-term thinking process. And so, as Stuart said, I got hired fairly early on in the process, and since that time we've been doing research on this. And I'm going to talk about some of the places that I've been and some of the research that I've done, and I'm always interested in more cool places that exemplify long-term thinking and or ideas from others, so please do bring them to me. The first thing I want to be clear about is what our scale is. Our scale isn't eternity. Our scale isn't astronomical time. So, you know, this is roughly, if you were looking at our little spiral arm of the universe, this is the kind of 20 billion year time scale of astronomic time. And we're not trying to solve problems on that time scale. This is a geologic time scale. This took 5 million years to create the Grand Canyon. This is still a few orders of magnitude out from where we're at. At 10,000 years, this idea of the long now basically as long as humans have had modern civilization, since the beginning of agriculture and later cities. And if you think about it in those terms, there's a lot of things that have survived on this time scale and human artifacts. And I'm just going to talk through at first why some of those things have lasted and why some of those things have not lasted. And all my examples are about things that have lasted. I think we have ample examples of things that haven't. But I do want to go over why things do deteriorate or get lost. And I broke it down into a few categories. Basically, water and air combined are probably the two major things. They destroy buildings, they destroy metal objects, they even destroy rock at some point as water gets into it and freezes in the winter, cracks the rock apart. And I'm going to talk a bit about a specific type of corrosion and oxidization called galvanic corrosion, and how we're working with that, and how we can look at history at how that's failed. It turns out that one of the ways that things don't last is they get lost. We know, for instance, that the Greek tragedies, many of the Greek tragedies that we have heard reference to, we don't have. And there's a ton of other things that we don't know if we've lost, right? So this is one of the worst ways. And then you can lose things and you can find them at the wrong time. So if, for instance, there was many Egyptian artifacts that were found during the expansionist era of England that were brought back just as ballast and dumped in the London harbor. They're theoretically still there, obelisks and things like that, but that was not a very good time for Egyptian artifacts to have been found. If they had been found later, they would have been much more prized. And/or things, sometimes they get found at a bad time in our ability to preserve them. And so that's another good thing to avoid. And then, of course, there's just plain old destruction. And the worst example of this is wars, but also we've seen it in the Buddhas of Bamiyan in Afghanistan, which were destroyed based on ideology that, of the ideologies in the world, Buddhism is a pretty benign one, but the Taliban still spent many days and many man-hours and a lot of munitions destroying these giant carved Buddhas. So that's probably the one that is the most kind of unworkable for us on our timescale. I don't know what we can do to solve that one, and we have a few strategies that I'm going to go over. And then there's this other funny one, which is that you just become unfashionable. And this is something that happened here in San Francisco, for instance, after all the beautiful Victorians were built. The 50s came around and they were looked at as old and funky and not modern, and they put up all these beautiful concrete tilt-up structures that we now have. And the last remaining Victorians we prize, but there's this problem of the product hype cycle. And many of you have seen this. This is the Gartner hype cycle. There's a technology trigger. There's the peak of inflated expectations. This is well before the product gets released, and the product gets released, and here's the iPad, where the trough of disillusionment when you don't know what to do with that thing. And then there's the slope of enlightenment, where people start figuring out, oh, well, I can sit on the couch and I can surf the web, and it's a great thing. And then there's the plateau of productivity, when people really start figuring out all the cool things they can do with their iPad. Now, you can look at this as just the iPad time cycle, or you can also look at this as even cultural artifacts or buildings and architecture, if you just decide that your time axis is much further. And so if you do the long-term version of the hype cycle, the thing that happens after acceptance, and this, you could have a time of utility, let's say a building or a big cultural artifact. This could be a century or more of acceptance and use, but eventually it declines, and then there's going to be some time where that thing becomes obsolete or unfashionable, and this is the most dangerous time. This is where things usually get lost and destroyed. So, for instance, the casing stones of the pyramids, or at least the pyramids, were looted not too long after they were loaded up with all the loot. And it just takes a few generations, usually 1 or 2 generations after the people who built it are gone, that the next generation just doesn't have the values and the same systems that their parents did, or it's a whole new culture that got brought in through war or some other cultural change, and they destroy that thing. But then comes this moment like now where those Egyptian artifacts or the pyramids are this priceless cultural treasure. And so how you bridge this trough of obsolescence, I think, is actually one of the largest challenges that Long now faces in how we make a 10,000-year object. So I'm going to talk about a few strategies for that. So why do things last? They're lost and they're found at the right time. As long as it is found again, then you're okay, and you're found at a time of good preservation. Sometimes you're just chemically lucky. So things that normally would not make it over the long term get buried in a particular type of soil that happens to mummify remains or something like that, and it just makes it. The dinosaurs that died in the La Brea tar pits were the ones that we were able to pull back out. Things are maintained. So there's a few things, and there's a few cultures in both England and in Japan and other places in the Far East where they've actually maintained things on a millennial time scale. And so you can actually build out of extremely vulnerable materials like wood and thatch and rice paper and have those things last for a very long time. And basically indefinite. There's things that are just made really, really tough. And so, we have pottery shards from tens of thousands of years ago, and we even have complete pots from tens of thousands of years ago. And these types of things can last. We have some metal objects from over 5,000 years ago, from the Bronze Age. And another technique is that they just take a really long time to complete. And that's one way of passing this trough of obsolescence, where if you're a cathedral, for instance, that takes 600 years to finish, that the generation that finishes it it's already transcended into this cultural icon. And then there's this funny one that's an emerging one, and I don't know what to do with it. But it's this ablative armor technique. And I'm going to talk a bit more about what that is and how I've seen it be successful. So in the chemically lucky category, we have things like this. This is a 5,500-year-old shoe made of leather, right? And so when people ask me about, what are you making the clock of the long now out of? It's like, how about leather, right? And this is a 5,500-year-old shoe. But the only reason this survived is it was found in Armenia, and it was buried in soil conditions that made it work. So we would either need to either need to bury it in those type of conditions, and it would be very difficult to visit, obviously, if it was all under dirt. Another chemically lucky thing, and a thing that got lost and found at the right time, was the Dead Sea Scrolls. And these date back to 150 BC, and they're still taking them apart with X-rays and finding new information on them. But they were sealed in a jar, I believe, a ceramic jar, and they made it 2,000 years basically by being lost. Another one that just had a good environment, and this is a good reason for caves and being underground, is some of the cave paintings. These are some of the more famous ones from Lascaux. These are over 17,300 years ago, made of pigments, mineral pigments. And since they're mineral pigments, they're made out of stone. The pigments themselves have survived, some better than others. But it's another good example of both chemically lucky and being lost. This one is actually one of the most intriguing ones to me, and it's a fairly recent discovery of mine. It doesn't really look like much here, but that's wood and lacquer that's over 2,000 years old. And it was found in a tomb in China where the whole thing was planked in cedar and then encased in white clay and then encased in 6 feet of activated charcoal and then white clay and then dirt again. And it was lost for over 2,000 years. And when they did find it, or I guess it was purposely buried for 2,000 years, they weren't really intending for people to find it, but when they did find it, the contents were in such good shape that they were able to perform an autopsy on the person who was buried there, for instance, and get everything out of their stomach. The cause of death was a heart attack. I mean, all the organs, everything was intact. And there's so they were sealed from the water with the clay, and then the activated charcoal did this neat effect. And one can only assume that they understood what this effect was. It's called a getter. And this is the same effect that keeps a vacuum in a vacuum tube, or at least originally did. And that activated charcoal is actually grabbing the air molecules out of the air and chemically bonding with them and making them not oxygen. So this became effectively an oxygen-free atmosphere that was preserved with very, very low technology for 2,000 years and would have gone on indefinitely, basically, if it had not been found. And we can presume that there's even more of these tombs left. But this is one of the few, and I point this one out because this is one of the few ones that actually I think was intentional, where they actually put in technology to have the remains and the organic matter last. So this is, again, wood that's 2,000 years old, not your usual multi-millennial material. And then there's the Bronze Age. So we have, this was Danny Hillis's original idea of Bronze Age technology, so to build this clock, or at least to maintain the clock. And items that are from 3300 BC, so 5,300 years old, have survived quite intact, some better than others. But bronze, and especially that early bronze, is actually not that metallurgically good. Yet some of it got chemically lucky in where it got lost and stored, and we have some of it not so much. But now with more modern techniques, you can certainly expect modern metals like certain stainless steels, titanium, things like that, to last on the order of 10,000 years in at least a decent free air environment. This is one that intrigued me and started making me think more about wood. And on our property in eastern Nevada, we have bristlecone pines, and they're an interesting one in and of themselves. They're a living object that can live for over 5,000 years. Or at least up to 5,000 years. And in fact, you can see where the rocks have eroded around their root structure by like 6 inches in 3,000 years. So the rocks are eroding faster than the wood there. But this beam, I'm about 8 stories up in the cupola of a cathedral in Ely, England, one of the worst places for a dry environment. And that beam right there, and that whole series of beams, the railings and stuff are all modern, but all the main structural elements holding this thing up are over 700 years old, and still doing just fine as long as they can keep the water out from the roof. And then I did a little bit of research into what the oldest wooden structure, still standing wooden structure in the world is, and of course it's in Japan, and it's this temple from 600 AD, so 1,400 years of constant maintenance. So all these fall into the category of you need an institution or a government or whatever that maintains things. And this one was clearly well maintained. And I'm going to bring up another one that was maintained in a different way. And another maintenance story is the Vatican. At one of our library conferences, we had the vice prefect from the Vatican Library here at Stanford, and when I went to Italy, he gave me this great tour behind the scenes of the Vatican Library. And we walked by this one room that had all these super flat drawers, and I asked what they were, and we went in and we opened the doors, and it looked like this. And it turns out that when they built St. Peter's Basilica, they made the artists do overruns of every color tile that they had to make for those mosaics, and apparently to quite a bit of protest, at least that was the story he told me, that they had to make all these extra tiles. And then they stored them, and to this day, they're still maintaining all of those mosaics 500 years later. And they do quite a bit of it. When I was leaving, they were just closing for Easter Mass, and only 45 minutes after they closed, all these mosaics had scaffolds up in front of them, and they had little guys in white bunny suits gluing little tiles in. So it's a pretty active process. So it made me think that actually if you walk around and look at the ground, you might be able to pick up your own tile at some point. So this is the other Japanese temple that's maintained in a different way than the last one. The last one was actually maintained. It's the same structure. This is the temple at Ise, which was one of the first things in this project that Stewart brought to my attention. And this is a very rare photograph that was taken when both the temples are erected at the same time. But basically, one temple gets deconstructed and another one gets reconstructed every 20 years. So once a generation, the master teaches an apprentice. These are Shinto temples. And so it's arguable that these kind of practices have helped the Shinto religion make it through the Buddhism coming across from China, and this actual physical embodiment of their religion has helped. The next one is scheduled to be finished in 2013. We were just talking about whether or not there was any damage in that construction from the earthquake. It'll be interesting to find out. But that would be a trip that I would like to make, is to see the commissioning of this. Apparently only the emperor and the emperor's family are allowed in, however. One of my favorite examples is the Antikythera device, if you've ever heard of it. Turns out this was an astronomical clock. It was lost off the coast of Antikythera, Greece, where it was found, and strangely, it's the only object like it that we found, and it brings back the date of when people think we invented things like differential gearing and a lot of the knowledge of the Western world of celestial mechanics and things like that by over 1,500 years in some cases, depending on the technology you're talking about. And with recent X-ray technology, they've been able to learn a lot more, and these guys in England and other places have done full reconstructions, and turns out it's a pretty advanced astronomical device. It clearly wasn't a one-off, because people must have built many prototypes to get to this stage, but no one's ever found anything like it that dates to that era. But it's a great example for us, building a 10,000-year clock, is that even if someone were to find it and it had been lost for a long time, that if we build it right, and it's this mechanical thing, that they might be able to reconstruct it if we give the right signals through the whole design. So the pyramids are an example of this ablative technique that I was going to talk about. And so ablative armor on a tank is sacrificial armor on a tank, or ablative paint on the bottom of a boat is a type of paint that sheds away as barnacles stick onto it. So this is a successful method that has been used in a couple places that I've found. And so the pyramids, while they originally had beautiful casing stones, they were filled with tombs and all kinds of riches, all those things were taken away. The outer casing stones were mined to be used in mosques in Cairo later, and the stuff inside was sacked quite soon. But the basic pyramidness of them is still there, right? So we still have that. So if you offer some kind of thing to be taken, maybe that is a new way to get something to last for a really long time. And another example, this isn't nearly as old, of course. These were only, the Taj Mahal was built in the 1600s, mid-16th century or mid-17th century. But it was encrusted with jewels all the way throughout all the hallways. And the final time the British sacked it, instead of burning this place or destroying it like a lot of other buildings that got destroyed of the imperial time of India, they spent a long time prying all those jewels out of the walls. And in fact, by the time they had finished that, they decided that the cultural artifact was clearly worth saving. It's hard to know if they would have saved it either way, but it again is this ablative technique of getting things to last for a really long time. And I mentioned cathedrals. This is one of the oldest cathedrals, and it took 600 years to build. This is in Cologne, Germany, and it's still being worked on. And we have a modern example of this, the Sagrada Familia in Barcelona by Gaudi. Was started in 1882. It's still under construction. They're hoping to be done with the next phase sometime around 2026, but that's sounding optimistic right now already. So we will see, but it's already past that threshold. This is already past that trough of obsolescence and unfashionable threshold. I think this thing will be saved I think it's already on a UNESCO object at this point. So now we get into a few examples where people were really intentional about building a 10,000-year space or longer, at least in a multi-millennial space. And so this is the exit of one of the tunnels at Yucca Mountain. Yucca Mountain is now closed as a nuclear waste site, but we'll see how long that remains. I think disasters like the recent one may change people's minds about storing spent material on site. We went and visited this. This is, when did we visit this, Stewart? 2000, I think. 2000, okay. And they give us an interesting tour. You get to ride in a little car all the way down. those blue access ramps are basically the only part of it that's, the blue access ramp up and down is basically the only thing that's done. They haven't dug any of the repository tunnels to my knowledge, but the idea there is that it can be stored. And one of the best things about this project is that they did a bunch of great federal research in in 10,000-year materials, both in nickel alloys, stainless steels, ceramics, glasses, all these things, and it's all publicly available, as well as concretes. And I'll mention the concrete again when we get to our site. This is an interesting one that I'm hoping to be my next visit. This is Onkalo Nuclear Waste Repository. All of the yellow part is actually already done. This is in Helsinki, Finland, or outside of Helsinki, Finland, and they have designed it with a 100,000-year time span. Recently, there was a documentary done on this, which I thought was pretty alarmist, but it's a pretty great engineering effort, and like the one in Nevada, they're great engineering solutions, and the two things that we walked away from there's two main lessons. One is that you can't solve a political problem with an engineering solution, and you can only engineer so many nines on the end of 99.9% sure it's going to be okay. And when you're trying to make guarantees for 10,000 years, it just doesn't work. Like there's always a hole in your theory of your 10,000-year theory. So it's actually vastly better to come up with a series of century theories than it is to come up with one 10,000-year theory. So the other thing that I'm learning in visiting some of these sites and seeing these pictures from Onkalo is that they're actually picking some of the same techniques we are. Arched roofs, drill and blasting done in a special way so it cuts from hole to hole. All those lines you see right there, it means that the explosive traveled from one hole to the next, to the next, to the next, and didn't overbreak the rock so that it doesn't last into the future and doesn't keep falling in on you. So that was good to see that their engineers came up with the same solution that we did. My most recent trip, which I did, I guess, a little less than a month ago, this is just 3 or 4 weeks ago, was to a site that was designed to last for 1,000 years, and it's in Svalbard. It was interesting. I saw the announcement, I think, that they were going to build this around 2005 and saw a little computer rendering of it, and in 2008 I saw an announcement that it was done. And I was just so shocked that they could build a 1,000-year seed vault in Svalbard in such a short time from design to completion. And that's me on the left and Steve Rowell on the right. Svalbard is a little island in archipelago about 2 hours north by plane of the most northern part of Norway. It's the northernmost and permanently inhabited place on the planet. You can get commercial flights into there. It's mostly they're basically subsidized by the Scandinavian government, but you can buy a ticket and go. And it's mostly a mining place. It's a coal mining island. On your approach, this is what it looks like. That's Svalbard Airport. This is probably the best weather that we had almost the entire trip right here. But it was still blowing 40 miles an hour across the runway and made for a pretty exciting landing. So they chose a different technique. They were trying to store seeds for all the seed banks in the world. And so instead of going to the high desert, in effect, this is a high desert. It actually has very low precipitation, but it's a high cold desert instead of a high hot desert. And it's not high, I guess it's at sea level, but it's high in latitude. The goal here was to find a place that was naturally cold enough to store the seeds, even if their cooling system failed. They target their cooling system for the seeds at -18 C, and the permafrost on Svalbard, even in summer, never gets above -5 C. So, and even at -5 C, the seeds can last for 20 or 30 years all on their own. There's also a funny arrangement of Svalbard politically that made it more accessible. You can kind of build things there that you wouldn't be able to build in other places. It has this funny treaty that was signed about 90 years ago that makes it kind of politically easy to work in. This is the design of the facility that I saw back in 2005, and I'll walk you through it. So this outside bit, those are the doors, and there's this kind of light art thing that shows up there at night when no one's really up there to see it, but there's some nice nighttime photos I've seen published of it. And so you go in the doors and you get to this tube, and this tube is apparently a special technology that was developed on Svalbard by the coal miners. This was the other interesting thing that I found out is they tried to build this in 2005 when it was the peak of the construction boom, and I still to this day haven't found someone to tell me why they had to have it done by 2008, but that was their goal. And so they couldn't find anyone to bid on the project at all. And so the only people that would bid on it were the coal mining companies on Svalbard. And so they had the coal mining companies build it. And the rock in Svalbard is just like crumbling schist. It just falls apart. So what they do to get through the permafrost is they do this thing called the Svalbard tube, which is this thing. And it goes through the most mobile part of the permafrost, which moves around a lot under freeze and thaw conditions. And you can see actually in the right side of this photo, or in the left side of the hallway, where it's already cracked. They've already had to do a bunch of renovations in this. And this is a downward sloping thing, which you can see from here, where this is a downward slope, and then it upward slopes at the bottom of that tube up to the seed vaults just slightly. And this is a lesson that we learned in other places as well. This is a retrofit. These are pumps. So what happens is that the frost builds up on the inside of these walls, then it thaws and it drops down to the floor, and then it runs down towards your seeds that can't be destroyed. So so then they put in these pumps. I had hoped to go here to learn a lot about engineering a 1,000-year facility from their efforts. I wasn't terribly encouraged by what I saw, except for this. Login book had signatures from Jimmy Carter, Ban Ki-moon, delegations from the US, Congress, all kinds of people. And it made me realize that even in the most ridiculously out-of-the-way, remote place you can go on the planet, people are going to want to come see your weird thing. And in fact, the harder you make to get there, the more likely they're going to want to come see your weird thing. And the weirder it is, the more they want to come and whatnot. So once you get through the doors, you get into this white concrete, which white underground, we've also found in other places, this is a good technique. This is called shotcrete, where they shoot concrete over the rock. They had to do it only in winter when it was frozen solid and the rock wasn't falling in on them. This is the kind of crosswise hallway that goes to those three back banks that you saw in the model. This is what one of the empty rooms look like. They've only filled one of them. And then looking back across the hallway, the frosty door there on the right is the one that's currently got seeds in it. You can see the frosty pipes going into it, cooling it from its ambient in this room is -5°C, and going into there it's -18°C. And they, basically it's all reliant on the coal plant on the island as well for that cooling. This was a cool thing that they did, is this is what when they turned on the lights when you're in there, but this is what it looks like when there's nobody there. This is just the emergency LED lighting. And I thought it was much nicer, actually. This is the door going in, and this is as far as we were told that we were ever going to get, actually. But they had to go in there and check on something. So we were lucky enough that they opened the doors, and we got to see a cage with a bunch of seeds in it. But they have these standard boxes for all the seeds, which you see, and then there's the USDA, which sends them cardboard on the left. Of course, the USDA decided not to do the standard box. But basically, I thought that this place was a reaction to genetically modified foods, where they were trying to store for this, genetically modified Armageddon that's clearly coming as far as Europe was concerned. But it's not it at all. They had started these seed vaults long before. In fact, there's another seed vault, a prototype one, that's in a container in another tunnel, an old coal mine in Svalbard. And they decided to do this largely just as a backup. So they only store replacement seeds for ones that are already in other seed banks, And they don't own them. The original place still owns them. You can get them back at any time. Everything that's in the seed bank is a public log, so you know what's there. This is what all the containers look like that they've received. Mostly now it's all these Mylar bags. So again, this is a purposeful 1,000-year facility, but I think this one's probably going to take a lot more maintenance. Luckily, I think they now have enough interest from all these different countries and people that interest for maintenance will be continued. Another one that was designed with a 1,000-year life that is an interesting one, and we learned a lot of lessons from as well, is the Mormon genealogical vault. And every Mormon that I had encountered, I had asked about this vault, and they all said, "Oh yeah, it's there. No, you can't go." And and it wasn't until actually Stewart got invited, I think, to give a talk at Brigham Young, and I said, "Okay, don't say yes. Wait, and say only if we can go see the vault." And they still wouldn't do it, but they said, if you both fly out to Salt Lake City and have lunch with the Mormon elders, we'll decide if you can see the vault. And so we did, and we had lunch at the top of the Joseph Smith Memorial Building in Salt Lake City with the elders, and we ate, I think it was buffalo burgers and deep fried pickles, and talked about archiving strategies and long-term thinking, and they decided we were good. And I got to about here before they took away my camera. And but they were really forthcoming. They gave us an excellent tour, and I've since found they've released some photos of the inside, and I think they've released a virtual tour now, which I couldn't find, but I saw references to. But this is what one of these tunnels. You see these tunnels in the background of this photo. They drilled and blasted tunnels going straight back, a series of 5 tunnels, and then did some crosswise tunnels and lined them again with kind of like the Svalbard tube, this metal tube, and then pumped concrete around it to stop the water from coming in, was the theory anyway. So this is the one that tunnels were getting drilled and blasted. I suppose these are Mormon architects. So this is my little drawing of what this place, kind of an overhead plan view of what this looks like. This front area is a work area where actually there was like 40 people work every day, all day. And then they have these series of vault doors, and then you go back, and then there's all the microfilm storage of all the genealogical records. And in the way back, they left it untubed, and they just put a little dam up, and actually the water's coming naturally through the rock, and they have their own reservoir, their own water supply for the whole facility, which they use for washing film, as well as just drinking and use there. So most of what the people were doing is this. So you can see the metal tube wall here. Again, white underground. There's no windows here, so they have a long work day. And then this is a photo I found of the vaults. So this is what all of those crosswise tubes look like filled with, and they are a lot of microfilm, all stored in the order that they were found, and the index is all in an Oracle database. So the thing that we learned here, and they were really nice at the end of this tour, they took us to a conference room and they rolled out all the plans on a table and let us look through the original blueprints, not take any pictures or anything, but they let us really look through it and see how it was all made. And then they also did a series of retrofits of the underground facility about 20 years in, because it started flooding. And this is the thing that we see with all these underground facilities, that they all try and keep the water out, and they all fail. So they put steel in, then they pumped concrete to seal the steel, but eventually it got to the welds, and then the welds, where the welding was, it attracts oxygen, then that rusted through and the water came in, and so the Mormon archive has actually flooded several times in its existence. They didn't keep stuff in the bottom drawers because of that, and then they also went in and they cut channels in the floor and ran the water out under. They have these giant nuclear-proof vault doors, and they have channels running underneath them for the water to come out. They realized that water was a more pressing concern than clearly Russia targeting them as a major cultural asset. So now I'm going to talk about some of the stuff about our clock. some of the stuff I'm going to show is stuff that we don't show really publicly, and we're under construction right now, and so our head is kind of down working on that. But in a small environment, I can show it all to you. But the first thing that we found out as we started researching how to get metals to last for a really long time is this notion of the galvanic series. And so the galvanic series is a listing of metals by their voltage potential. And so platinum is very high, would be considered a 0, and then as you go down into things like aluminum, if you've ever seen what a copper penny sitting on top of a aluminum boat in salt water does, that penny will go right through it in a few months. That is galvanic corrosion. So basically, you've got dissimilar metals that are far apart on the galvanic series, and then you put an electrolyte of salt water on it, and it burns through. And so we spoke with a lot. We've worked with a lot of material scientists, and finally, in one conversation, the guy said, "Everything is burning. It's just a question of how fast." And so everything is subject to this effect. And so you have, even in air, air can be an electrolyte, as lightning proves. And so you always have this effect. If there's a little bit of salt in the air, then it's even worse. But you want to use things that are very high on this scale, and when you put them right up against each other, if you do it at all, you want to use things that are very close on that scale, if not identical on that scale. So you'll see that most of the things that we make on the clock, most of the things in this room, in fact, except for the short-term prototypes, are all made out of things like Manel, 316 stainless, titanium. We're staying out of the silver on up scale just to make it less of a nuisance to be stolen. This is one of the most recent parts that we just finished on the clock. This is an 8 or 9 foot diameter gear. It uses a special cycloidal pattern that's actually, every single one of those teeth is 3-dimensionally carved, and it goes into a special roller that rolls in such a way that there's never a moment where anything's scrubbing. So the other type of destruction that can happen to two metals is that as they rub up against each other, you can get micro welding, or another effect called galling, where it rubs away a bit of metal, and then they slowly just kind of get destroyed. The other way to fix galvanic corrosion is to isolate things electrically. And I'll pass this around. I need it back, though. This is that's a silicon nitride ceramic ball bearing that's being used in the clock. And this is a different type. This is an aluminum oxide type of ceramic ball bearing. But this is what turns that big gear that you just saw. These are, in fact, we just mounted it up last week on these bearings. But as you can see, the two types of metals, we're using an A286 stainless, a hard shaft, and we're using a 316 stainless outside. Even though they're very close on the galvanic scale, if we can separate them with this isolator, then they don't cause that galvanic corrosion. The other thing that happens with bearings is that when they sit and you have point load the metal, as they sit there and they just micro weld from small vibrations. And if it's not metal, it can't weld. Or it can't gall. And so we've been testing these ceramic bearings with no lubrication, now passing 4 million cycles. We can't test them very fast because they build up heat and they can't shed it, but none of our things move very fast. But we had hoped that we could do very fast accelerated aging or accelerated tests, but it's taken us several months just to get to 4 million cycles. We think some of the fastest parts of the clock basically would get to 6 million cycles. So far, these bearings look like they're going to make it. That big gear that I showed you goes in this mechanism. This is the power system for the clock. So there's those big gears right there. There's 3 of them, and they're the main differentials for winding the clock. Underneath there, that big cylinder is a weight that's hanging from this kind of spine-like rack gear that goes up through the center. And as you walk around that capstan, you're winding that weight up to the top. And most of this is now under construction, most of it being built up in Seattle. I just shot this picture today at the assembly shop. All the parts are being machined in different shops and then coming to coming to our shop in San Rafael. That's Chris Rand, the lead machinist. He's been on the project basically as long as I have. I hired him, I think, in '97, and he built pretty much all the things in this room. And the first prototype in the Science Museum. And again, this is, so the ball that I'm passing around is a silicon nitride silicon nitride ceramic ball that is the bearing for, one of the ball bearings for this device, which is the full-scale Geneva. And if you get a chance, there's the chime generator around the corner. That's the part of the clock that can ring a series of 10 bells in a different sequence each day for 10,000 years. So the most revolutions one of these things would go around is 4 million cycles. So all of these things are well within the realm of normal tested products, but it's rare that nobody ever tests them this slow, basically, or with no lubrication. So we've had to do some of our own testing to discover that. And the no lubrication thing is that lubrication attracts dirt, and basically you can't rely on lubrication always being there because it goes away. We actually have a really complex thing to do underground in rock, and it turned out that there was no technology to do this. You can drill and blast, and it's really rough. You can use quarrying techniques, but it's really slow. But there's been recent developments in quarrying. And so this is Carrara, Italy. That's a road there. It's like huge trucks can go on it. This is similar. It's marbleized limestone. And in the last basically 10 years, they've developed diamond saw technology that can cut through stone basically faster than you would normally associate cutting through wood. And what nobody has done, however, they made these saws, these gallery saws, which cut spaces like this that are on hydraulics, and they just do one cut and they reset them up to do another cut. But what nobody has done has roboticized this whole thing. And I have a background in building robots for the BattleBots competition, so it was fun to finally have a combination of my Long Now background and my BattleBots background into building a 9-foot diamond chainsaw that can cut stone. This was built by Stewart Kendall of Seattle Solstice. They made the base of the orrery, which you should check out underneath there. And we've just been doing more tests with it, and just 3 days ago I was up there, and now it's got all the new KUKA robotics controls, and it's actually cutting 3-dimensional curves. And the idea is that it's going to be able to do this for us in that vertical tunnel. And then you break away each layer in between your cut, and you get this kind of smooth, rough finish. And you do that for about a year, and you get a spiral staircase in solid rock with no overbreak. So that's what we're heading towards right now. That's kind of what a guy would look like on it. It'll have a big cart. It's actually going to be it's going to be kind of a 2-story cart, really. So what have we learned? We learned that we should make it remote enough that you're not near a city that gets bombed. We have learned that water is going to get in. We have to route water away from it. Even the design of those stairs, we designed droop into that saw so that as it's cutting, any water that comes down the walls gets onto those stairs and then runs away and then down the outside spiral of the stairs and all the way down. So, and all the entrances that you see, those tunnels that we're making, are slightly uphill. All the other ones from up go down, and so the whole thing drains always outward. So we assume that water will get in. Our goal is to keep it away from the clock mechanism and then let it run out. Oxidization control, so things like encasing really delicate things, so the escapement and the pendulum are going to be encased in glass, basically, a very thick quartz glass, and use metals that are high in the galvanic. Avoid welding for that reason that we talked about in the tunnels at the Mormon area. We are using welding. We couldn't avoid it in some places, but what we do is we kind of slot the metal together first, so it's kind of puzzle pieced together, so that even if the welds fail, it's mechanically can't push through itself, and then we passivate those welds by dipping the whole thing in acid, and you get all that free oxygen off the surface. And so there's some techniques you can use welding for. Design it to be lost. So a lot of the clock mechanism is basically designed to, even if no one's there, and it doesn't get wound and the clock stops or the dials aren't moving, that when you find it, you'd be able to figure out how to make it work and wind it back up and get it all back up to the right time. And so things like that orrery are a good example of that, where one of the dials of the clock, some of the dials of the clock are showing natural cycles of time, so that you can look at the sky, look at this thing that's broken, and rectify the two. Make it difficult to disassemble and take it out of there. So this is, we're basically going to build this thing as a ship in a bottle. It's going to have two ends to it, and it's all going to be encased once it's done, and then and everything's going to get built in a way that you'd have to basically disassemble the whole thing to get it out of there. It doesn't stop somebody who's trying to mine it for the metals, but hopefully it'll slow them down long enough that we can cross that chasm of unfashionability. The other thing is to use more ceramics, and we're trying to find ways to use more ceramics. Things like the bells, we're looking at using ceramics, and one of the first things that's always pillaged out of the European churches is the big bronze bells to be melted down for wars. So ceramic bells are a great one, and just the bells are so easy to steal. They're always hanging from something that can, it's like a little teeny hinge, and you just cut it loose, and there it goes, right? So, but ceramics are kind of worthless in and of themselves. They can't be remade into other things. Really, the casings on the outside of the pyramids were certainly carved, recarved, but a tube of ceramic would be a bit harder to do. So it's using materials as smart as you can like that. The other one is to design the long-term institution, and we're still trying to figure that one out. That's the Long Now Foundation, and it's certainly going to be the technique that's used at places like that Svalbard seed bank. It's going to need that kind of institution surviving alongside it. And this ablative layer one is the one that we don't know what we're going to do with yet. But should we encase the tunnel with jewels or gold or something that people will steal and think that they have taken the value from this thing? I don't know. But thank you. That's all we've learned so far.